The topic that we will be talking about today is the consequences of energy transfer. And we've already discussed the three modes of energy transfer: convection, conduction, and radiation. In this one, we will just be talking about the applications and how we can observe uh, heat transfer through conduction, through convection, and through radiation in our daily lives. So, talking about conduction, the engine of a car is turned on and the hood becomes warm due to the conduction of heat from the engine to the hood of the car. Similarly, when an ice cube of when an ice cube is placed into the hand of a person, over time, heat conducted from a man's hand to the ice cube will cause the ice to melt. So, we're right now talking about conduction mainly, and okay, so let's just say that we have, sorry, yeah. Okay, so initially we're talking about the hood of the car. Why does the hood or the bonnet of the car get hot eventually when it is in the sun, or why do we say that the engine warms up? So if this is basically the engine of the car with all the equipment and everything, uh, and it has a fan, and it just basically an engine. Okay, it's just a random drawing. So the engine warms up, and obviously, because it is working on friction and a lot of gears, so they are producing some friction and heat energy. So, although the bonnet is not directly attached to or is not touching the engine directly, but there are some several pipe networks and other things, or even if it is not touching it, it transfers heat from a region of lower energy or lower temperature, from a region of high temperature region that is closer to, let's just say, this region which is closer to the engine, to a region which is not that close to the engine. So eventually what happens is that heat transfers throughout the hood or the bonnet, and it gets completely warm. So that is through conduction. This was a kind of a complicated example, but if you think about some very easier or very simpler examples that we see in our daily lives, for example, let's say if there was a person who has some ice melts in his hand. So this is a hand, and a person has ice in their hand. So there are two ways you can experience conduction. First thing is that the person immediately feels cold. That is because that his hand is warm and the ice is cold, so there's a difference in temperature, and that temperature difference causes him to feel this cold. The other thing is that um, although the ice is not put in some heater or is not given some very direct, powerful source of heat, the temperature gradient, by temperature gradient I mean that the temperature difference, that if there's a body, if this is a temperature gradient, let's say, and we are measuring temperature from this side, and if there's a body whose temperature is over here, but then there's a body whose temperature is over here, so this slope is basically the temperature gradient. And the temperature gradient for conduction is that it flows from a region of high temperature to a region of low temperature. So obviously, the hands might not even seem that hot for if some other person touches them, because of the temperature gradient in that scenario would not be that steep. But in this case, since ice is at a very lower temperature, uh, so the temperature gradient is steeper, and thus it causes the ice to melt in the hands. I'm going to explain the concept of temperature gradient again. So basically, what happens is that there are two temperature gradients. In the first one, the in this one there are two people handshake. So it's handshake, and in this one ice in hands. What happens is that when two people handshake, although there is a very huge chance that the first person has a temperature over here and the second person has a temperature over here. So there is a temperature gradient, and it is like this. And the two people will feel that difference in temperature, but it will not cause a significant uh, effect when they both when the two surfaces meet or when they both shake their hands. However, when the ice is at such a lower temperature and the person's hand are at a relatively high temperature, like this is the same temperature. So in this case, the gradient is so much steeper. Hence, there is a transfer of heat. Hence, we experience conduction, and hence the ice melts. And some other examples of conductions are that a boy places a hot dog on the end of an unraveled metal um, clothes hanger, and he begins to cook it over fire. After a time, after a time, the hanger begins to feel hot due to the heat conducted from the hot fire all along the piece of wire. So, since metal is a better conductor of electricity as well as heat, so it's the process of conduction in hot wire or in hot hanger is far more sudden, and it's far more drastic than in other materials. So when a piece of hot lasagna is placed on a porcelain plate, the plate is feel will feel warm to touch after several minutes due to the conduction of heat from the just cooked food on the plate. So similarly, these are some examples that basically take place in our daily life, and we observe them. But what happens is that now you can put in perspective that where is conduction exactly happening. So a young boy inside after playing on a snowy day and huddles up to his mother to become warm. It is basically heat is transferred from his mother's body to his own through a process of conduction. So if you hug someone in normal days, it won't feel that drastic because of again the concept of temperature gradient. However, in this case, since the young boy comes inside after playing from a snowy day, so his temperature is already pretty low. So when he huddles up to his mother, the he immediately feels warm because of the temperature gradient. So that also happens because of the process of conduction. Everyday application of conduction of heat. So these are some examples of conduction of heat. The first one is frying of eggs. That basically the way we cook our things, literally every time it depends on the process of conduction, because we have an immediate open source of fire that we and then we put a utensil on it, and then it conducts heat, and that's why our food basically gets cooked. So in this case, the way the omelets are being made are also through conduction, and then in even vacuum flasks, this layer is made up of metal, so it is basically conducting the heat and keeping it inside. And again, we wear warm gloves and etc. so that we can feel conducted and insulated. So these are examples of conduction in our daily life. Now we've talked about I'll add an N here. Now we've talked about conduction. Now let's go towards convection and its application. As we've seen that conduction happens all around us, convection also does happen all around us. The following are the uses of convection. Car engines are cooled by convection currents in the water pipes. Water is a very good substance to carry the unwanted heat away from the engine to the radiator. Most of the daily applications where we use the word radiator, let's just say heater, when we have room heaters, we call them radiators. But basically, they're actually just working on the concept of convection. Similarly, behind the refrigerator, we have radiators, And even inside our car engines, we have radiators. But those radiators are basically using the concept of convection. So what happens is that engine warms up, and then there's this pipe network, which in turn gets recycled and gets into the engine again. So what happens is that in this whole procedure, water is taking away the heat, and since hot water rises or hot currents rises, so that property basically causes it to move upward, and then as it cools down eventually, because water is a very good substance to carry the unwanted heat away because it has a very huge specific heat capacity. So eventually, as it cools down, then the density of the water significantly increases and it comes down. So it's the complete process of convection that causes the heating in the engines to be regulated through the radiator or these pipe networks. Similarly, the land and sea breezes, they're also caused by convection currents, and we're going to discuss that later on in this slide. Similarly, rising air over the land are convection currents and are used by glider pilots to keep their gliders in the sky. So basically, the temperature gradient that is carried away by air or water, the whole concept depends on the convection currents and the process of convection. That the hot air or the hot substance or the hot water is taken up and the cold one then sinks down. So it's like a circular cyclic process which can be used or made use of um, in different processes. Similarly, as they're talking about the glider pilots or the gliders in the sky, they make use of this whole process too. Um, Similarly, air conditioners are installed near the ceiling of the room to allow the setting up of convection currents. Now, why are they installed near the ceiling? Because we have discussed that the hot air rises and the air sinks. And the reason why we install air conditioner is because we want cooler air. So the cooler air sinks. So the cooler air basically sinks, and the hot air that is not that conditioned or is not at that lower temperature, it rises above. As it says that to allow the setting up of convection currents, the air conditioner releases cool, dry air into the room. As cool air is denser, it sinks. The warm air, being less dense, rises. The air circulates around the room, and the temperature of the air will eventually fall to the desired value. Similarly, when this whole process of hot air rising and the cold air sinking becomes the difference between their temperatures becomes very, very minimal, there is a state of equilibrium that forms in the room, and the temperature of the room is at a stable point. Okay, now we've talked about how land breezes and sea breezes are a very huge example of convection and how they control the temperature in those areas majorly. So what happens is that land and sea breezes are a result of convection. We've talked about that. So on a hot day, the temperature of the land increases more quickly than that of sea. Again, we've talked about that in regards to the conductive properties or the specific heat capacity of and uh, land and sea land and sea. As so what happens is that the temperature of the land increases more quickly than the sea. It is because the specific heat of land is much smaller as compared to water. So the land heats up more quickly than water. Although they're both exposed to the same temperature, the land heats up quickly than that of water. So the air above land gets hot and it rises up. Cold air from the sea begins to move towards the land, and it is called a sea breeze. So, same temperature, this remains cold, this gets hot very easily. So, the hot air rises over here, which causes a low pressure, and then as it rises above to the clouds, eventually it gets cold. The hot air that was initially risen from the land or from the area, so it gets hot, and when it rises up to the clouds, eventually it reaches this point where it is at equilibrium, and then it gets cooler eventually. So its density increases and then it sinks again. So this process is again cyclic, and it causes the process of sea breezes and land breezes. Okay, now we've talked about the applications of convection and conduction. We'll move forward to the applications of radiation in different aspects of our daily life. Two things that are really important are in the syllabus are a vacuum thermos flask, and the next thing is the greenhouse effect and how does it actually happen. So a vacuum or a thermos flask keeps hot liquids hot and cold liquids cold. It is very difficult for heat to travel in and out of the flask. Now the reason is that we have to the modes that are governing this process are again convection, conduction, and radiation. So the transfer by conduction and convection is minimized by making the flask a double-walled glass vessel within a vacuum between the walls. So if we have a vacuum, what vacuum does is we have already discussed that vacuum prevents any kind of conduction through conduction or convection. So if we have a vacuum in between two walls, there is a very high chance that the second wall is not going to conduct any heat at all because there is no medium whatsoever to carry that heat. Radiation is reduced by silvering both walls on the vacuum side. Now, the things that governed conduction and convection were the medium or the currents or the solid itself, and the thing that governed radiation was the kind of material or the kind of surface. So, in order to have minimized radiation, what we do is that the inside of the vacuum flask is made up of a silvery glazed material. So, radiation is reduced by silvering both walls on the vacuum inside. Then, if, for example, a hot liquid is stored, the small amount of radiation from the hot inside the wall is reflected back to the vacuum and it stores the heat inside. So, by this, across the vacuum by silvering on the outer wall. The slight heat loss that does occur is by conduction up the thin glass walls and through the stopper. So, since we do need an opening from which we can drink from the thermos flask, so that is the only thing that is left for any kind of heat transfer to take place, and thus that causes a little slack or lag in the insulation. And this heat loss is again caused by the conduction mechanism. But again, since these walls are made up of glass and glass is not the best conductor, so it is again very thought out and very minimized. This is the whole diagram. It shows silvered surfaces, and there's the vacuum inside. So this glass inside, and then this is again the silver lining that causes the radiation to be minimized so that it is reflected inside. And the vacuum between the two walls, this initial wall over here and then this wall over here. So it's basically causing minimum heat to get lost, and so that the temperature of the liquid inside the thermos is maintained easily. Now, the next thing to discuss is the greenhouse effect, and again, it uses a very fair amount of radiation as well as conduction, etc. So, the warmth from the sun is not cut off by the sheet of glass, but the warmth from a red hot wire can be blocked by glass. The radiation from very hot bodies like the sun is mostly in the form of light and short wavelength infrared. So that means that we're going to talk about radiations. The radiation from less hot objects like a fire um, is largely long wavelength infrared radiation, which, unlike light and short wavelength infrared, cannot pass through the glass. Light and short wavelengths infrared from the sun penetrate the glass of greenhouse and are absorbed by the soil, plants, etc., raising the temperature. This in turn emits infrared, but of their relatively low temperature. This has a long wavelength and is not transmitted by the glass. The greenhouse then acts as a heat trap as its temperature rises. Carbon dioxide and other gases, such as methane in the Earth's atmosphere, act in a similar way to the gas of the greenhouse in trapping heat. Thus, this has a serious implication on the global climate. Now, we've talked about the greenhouse effect in which glass is being used to trap the heat inside, and it can enter from the sun because of the larger wavelength, but it cannot go out because of the smaller wavelength, but it cannot go out because heat in the form that is released by the fans is in a different wavelength that cannot go outside. So we're receiving the incoming waves, but we cannot let them out. So that causes the heat to basically capture inside and be warmer for a longer time. So it's basically analogous to the behavior of carbon dioxide, that it behaves in a way that it forms this greenhouse blanket or glass around the earth, and it traps the heat inside, which can cause a very huge effect on the global climate.